Welcome to the session 1 of Unit 3 Dynamics of Fluid Flow or Fluid Mechanics. Fluid mechanics is a study of fluid which is in motion, where the fluid forces which are responsible for the motion of the fluids are considered. In dynamics, a Newton's second law is applied for incompressible and non-viscous fluids. Incompressible fluid means the density, that is rho, is constant, and non-viscous fluid means which has a less or no friction. We all know what is Newton's second law of motion. It is force is equals to mass into acceleration. Here I have considered in the direction of x, hence it is Fx, that is the force exerting or force acting on a fluid element in the direction of x is equals to mass of the fluid element into acceleration in x direction. See, there are various forces which are responsible for the fluid motion, namely gravity force, pressure force, turbulence force, viscosity force, and compressibility force. Since we are uh, applying the Newton's second law of motion for incompressible fluid and non-viscous fluid, so here, see here, Fx is the total net force acting in the direction of x. It is the sum of gravity force, pressure force, turbulent force, viscosity force, and compressibility force. Here, Fc of x is neglected because we are applying the Newton's second law of motion for incompressible fluid, that is rho equal to constant. So the above expression reduces to Fx is equals to Fg plus Fp plus Ft plus Fv. Okay, so this equation is called as Reynolds equation. Again, in this Reynolds equation, if we neglect this viscosity force, then we will get the Euler's force of motion, which is the summation of gravity force, pressure force, and turbulence force. Let us see what are the assumptions made while deriving the Euler's equation. So there are three assumptions. One is the fluid is non-viscous, homogeneous, incompressible, and irrotational. If we talk about a fluid flow, a fluid flow, it should be a steady flow, uniform flow along a streamline, and no external energy or external force are involved in this motion. Okay, these are some of the assumptions should be adopted while deriving the Euler's equation of motion. Okay, so this is let us derive the Euler's equation of motion. Here in this figure, consider the fluid flow in the direction of S. Okay, let us consider a streamline that is in the direction of S. So in that, let us consider a cylindrical fluid element which is having a length of ds and area of dA. Got it? So here the Euler's equation is derived for a steady flow of an ideal fluid, okay, along a streamline. Next, by considering what are the forces acting on the fluid element, we can see here the first force, that is along the direction of the flow. Since we know that force is equals to pressure into area, so I'll take the first force, that is F1 force, which is equal to pressure P into area of the cylindrical element dA. The another force is F2, which is acting in the opposite direction of flow. So which can be taken as F is equals to P plus dou P by dou S into ds, whole thing into dA. One more force is acting, that is the weight of the fluid element, which can be taken as mass into acceleration due to gravity. Again, this mass can be replaced by density into volume. So again, that volume can be replaced as area into length of the fluid element. So we will get weight as rho into dA into ds into g. So let us assume this is the theta is the angle. It is the angle between the direction of flow and action of weight of an element. You can see here this is the theta is the angle between this is the direction of flow and this is the weight acting, the weight of the fluid element acting in the downward direction. By applying the Newton's second law of motion, the resultant force of the fluid element in the direction of S must be equal to, again we can take it as Fx is equals to m into A. So Fx, we have to consider all the forces which is acting in the x direction. So here in this figure you can see this is the one force and this is the second force and the third force is the weight component. Say you have to resolve it. Okay, since you if you resolve it you will get the weight component force acting in the x direction. So if I take this as capital W, so W cos theta is the component force in the direction of flow, that is in the x direction. So you can see in this equation, which is equal to mass into acceleration due to gravity. Here rho dA ds is the mass into acceleration due to gravity is as. So there are three forces you can see here. P into dA minus P plus dou P by dou S into ds into dA minus W cos theta. This is the component force in the x direction of the that is weight of the fluid element, which is equals to mass into acceleration due to gravity. So further we'll get the equation as like this. So here in this equation, let us see what is AS. AS is the acceleration due to gravity in the S direction. So again we can write this AS as dV by dt. A is the acceleration. It is nothing but rate of change of velocity. If you partially differentiate this velocity, then we will get it as dou V by dou S into ds by dt plus dou V by dou t into dt by dt will be equal to 0. Since the flow is steady, we can say this dV, uh, this dt gets cancelled, it will be equal to 1. Got it? So and we can say this dou v by dou t, that is the velocity, which will be equal to 0. So the above equation reduces to this factors gets cancelled. Since dou v by dou t equal to 0, because the flow is steady, this this factor will get cancelled and we will get it as dv by dt is equals to dou v by dou s into, instead of ds by dt, this is nothing but rate of change of displacement, we can rewrite it as v, which is equals to A. Okay. Substituting this equation 2 in equation 1. In this equation 1, if you substitute the value of AS here, okay, so you will get this equation. If you divide this whole equation by rho into dA ds, we will get this equation. Got it? So, dou P by rho plus G into dz plus V into dou V equal to 0 is called as Euler's equation of motion. If you integrate the Euler's equation of motion, we will arrive as the equation as P by rho plus G into Z plus V square by 2 equal to 0. Divide this equation throughout by G, we will get this equation. Okay. So, the equation reduces to P by rho G plus Z plus V square by 2G. It is 2G equal to C. This equation is called as Bernoulli's equation. So here P by rho G is nothing but pressure head, Z is the potential head and V square by 2G is the kinetic head. Let us see what is the statement of Bernoulli's theorem. So again, it is also applicable for a steady ideal flow of an compressible fluid, where you can see the total energy or any point of the fluid is considered to be a constant. The total energy consists of pressure energy, kinetic energy, and potential energy. Let us solve some problems on this Bernoulli's and Euler's equation of motion. I'll read out the problem. The first problem: water is flowing through a pipe of 15 centimeter dia is given under a pressure of 30 Newton per centimeter square. Pressure is given with a mean velocity 3 meter per second. Find the total head or total energy per unit weight of water at a second 5 meter above the datum line. So let us see what and all the things are given. Diameter is given d, so you can determine from the diameter, you can determine the area. And pressure value is given. It is given in centimeter square. You have to convert it into meter square, so it will become 30 into 10 power 4 Newton per meter square. Velocity is given. Okay, then what else to be find out? Given that is the datum line, datum head is given, that is 5 meter, which is nothing but the z value is given. From the Bernoulli's theorem, we have this formula: P by rho g plus z plus v square by 2g is equals to total energy. If you apply all the given things in this, P is given, rho you know it, since it is a water, it is 1000 kg per meter cube, g is 9.81, plus z value is given, that is 5 meter, you can substitute directly, plus v square by 2g, v square velocity is given 2 into g, you will get the total energy. Unit is meters. Okay, 36.038 meters of water. Next problem: the pipe through which water is flowing having point 2 and point 1 at section 1 and 2 respectively. Okay, the velocity of water at section 1 is 5 meter per second. Determine the velocity head at section 1 and 2 and rate of discharge. You have to determine the velocity head, which is nothing but v square by 2g at section 1 and 2. Rate of discharge is q. Okay. Diameter is given, that is point 2 is d1 and point 1 is d2. At section they have taken two sections. At section 1 it is point 2 and at section 2 it is point 1. So you can determine the area a1 and a2, you can determine. The velocity at section 1 is given, that is v1 is given, you need to determine v2 to determine the velocity head at section 1 and 2. Got it? So we know we have a continuity equation. From this you can determine what is v2. Got it? So after that, let us determine what is velocity head at section 2 and velocity head at section 1 also you can determine. Then determine what is q1 and q2, that is the discharge. Very easy problem. Thank you.